Ever wished you could like hit a dough on an AI's decision?
Uh,
Like rewind its thought process and see exactly how it got there.
yeah,
Seems pretty sci-fi, right?
it does. But turns out that concept is tied to some pretty hardcore math, and
Okay.
that's what we're going to be diving into today.
All right. So math it is. I guess today we're looking at this 2021 paper
Yeah.
that kind of throws a bit of a wrench into the world of transformers.
Hmm.
Those AI superstars behind, well, everything from language translation to image generation.
Everything these days.
Yeah, exactly. So,
The paper's called The Lipschitz Constant of Self-Attention, and
okay.
it really tackles this like fundamental issue
Hmm.
with how transformers are built,
Okay.
specifically their reliance on something called dot product self-attention.
All right. I'm already sensing we're heading into some like abstract territory here.
Yeah.
What exactly is this Lipschitz thing and why should I care?
So imagine you're stretching a rubber sheet.
Okay.
In a Lipschitz continuous system, no matter how much you like pull or distort that sheet, points that were close together initially stay relatively close.
So it's about maintaining a certain level of smoothness even under pressure.
Exactly.
Okay.
Now, I think of the neural network as that rubber sheet.
Okay.
And the input data as the forces acting on it,
Right.
Lipschitz continuity ensures the output of the network.
Yeah.
Doesn't go haywire with even like tiny changes to the input.
Yeah. And why is that so important for AI?
So this property is crucial for building like stable and predictable models.
Mm-hmm.
And as this paper argues, it's essential if we want to create invertible neural networks.
Okay. So those are the endo buttons we were talking about earlier.
Yes.
So where does self-attention fit all of this?
So self-attention is this mechanism that lets transformers analyze relationships
Okay.
between different parts of a sequence,
Mm-hmm.
like how words in a sentence relate to each other.
Right.
It's really what gives them that uncanny ability to grasp context.
But this is also where things get kind of tricky, according to this paper, right?
Yeah, they demonstrate mathematically that the typical dot product self-attention
Yeah.
is not inherently Lipschitz continuous.
Hold on, let's back up for a sec before we jump into the problem.
Sure.
Can we just break down exactly what happens in dot product self-attention?
Yeah, so imagine you have a sequence of words.
Okay.
Self-attention calculates a score for each word pair, reflecting how much they attend to each other. The higher the score, the stronger the connection.
Right.
And this score is based on the dot product of vectors representing those words.
So if the words are similar, their vectors point in roughly the same direction,
Yeah.
resulting in a high dot product and strong attention.
Exactly. And this mechanism is powerful,
Okay.
allows the model to learn complex relationships within the sequence.
Hmm.
But the authors uncover a critical flaw in this approach
Okay.
when it comes to Lipschitz continuity.
What that flaw is.
So think back to our rubber sheet analogy.
Okay.
With dot product attention, you can create these pinch points where the output becomes extremely sensitive to even tiny input changes.
So our smooth sheet is no longer so smooth.
Right.
So what does that mean in practice?
It means you can't guarantee bounded output change,
Mm-hmm.
even for a tiny input tweak.
Okay.
In other words, the model's behavior can become unpredictable
Yeah.
and erratic, especially as you increase the complexity and depth of the network.
And this throws a wrench into the whole invertibility idea because,
Yeah, because for a network to be truly invertible,
yeah,
you need that like precise and predictable relationship between input and output.
right.
Without Lipschitz continuity, you lose that guarantee.
No.
It's like trying to rewind a video that's been corrupted.
Yeah.
You can't be sure you'll get back to the original.
Right. Okay.
Yeah,
So dot product attention, the workhorse of transformers, has this hidden Achilles heel.
it does.
So what did the authors of this paper propose as a solution?
They introduced a new type of self-attention called L2 self-attention.
L2 as in like Euclidean distance.
Yeah.
Like that stuff you learn in high school geometry?
Exactly. Instead of relying on dot products to calculate those attention scores,
Mm-hmm.
they use the L2 distance between vectors.
So instead of measuring how aligned two vectors are, we're now looking at how far apart they are in space.
Precisely. And while it might seem a small tweak,
Yeah.
it has some pretty profound implications for Lipschitz continuity.
Okay, I'm all ears. Walk me through the logic here.
So the key insight is that L2 distance, by its very nature,
Mm-hmm.
enforces a limit on how much the output changes
Okay,
based on the input variations.
right?
Even if one vector shifts dramatically,
Yeah.
the L2 distance to other vectors will only change in a bounded way.
It's like setting up a safety net,
Yeah,
preventing those wild swings we saw with the dot product attention.
exactly. And the beauty is they don't just propose this idea.
Right.
They mathematically prove that L2 self-attention is Lipschitz continuous.
Wow.
They even calculate an upper bound on the Lipschitz constant,
Okay.
which is really essential for building invertible networks.
So problem solved. Can we now build transformers that can run in reverse,
Wow.
perfectly reconstructing the input?
There's a bit of a catch.
Okay, there's always a catch.
To guarantee this Lipschitz continuity with L2 self-attention,
Yeah.
they had to impose a constraint on the model's architecture.
A constraint. What kind of constraint?
So they had to tie the query and key weights
Okay.
within the self-attention
Hold on.
reservoir.
Remind me what those queries and keys are all about again.
Think of it like searching for information.
Okay.
Your query is what you type into the search bar.
Okay.
And the keys are the labels attached to each piece of information
Right.
in the database.
Mm-hmm.
Self-attention uses this analogy to determine which parts of a sequence are most relevant to each other.
So if I'm understanding this correctly, by tying the query and key weights together,
Yeah,
we're essentially reducing the number of free parameters the model can learn.
that's right. It's a trade-off.
Okay.
You gain Lipschitz continuity and the potential for invertibility.
Right.
You might potentially sacrifice some of the model's expressiveness and flexibility.
Did they actually test this out in practice?
They did.
Did this L2 self-attention thing actually work?
Yeah, they built a transformer using L2 self-attention
Okay.
and tested it on a classic task, character-level language modeling,
Okay.
which basically means predicting the next character in a sequence.
Kind of like AI autocomplete. Right.
And what's remarkable is that when they simply swapped out dot product attention
Yeah.
with L2 attention, the performance was virtually identical.
So at least for this specific task, the L2 version held its own.
Yeah.
Against the standard dot product approach,
It did.
even with that added constraint.
Yeah, that's right.
Okay.
But things got more interesting when they tried to make the model fully invertible.
Okay, how's that?
With the same number of layers as the original transformer, the invertible version did show a dip in performance.
So there was a price to pay for invertibility?
It seems so.
Okay.
However, they found that they could recover that lost performance by simply adding more layers.
So you can have your reversible cake and eat it too, as long as you're willing to bake a bigger one.
Precisely. But here's where it gets really intriguing.
Okay, lay it on me.
The invertible self-attention led to significantly more stable training. Stable how?
They could use a fixed learning rate and still successfully train very deep models, something that's notoriously difficult with traditional transformers.
So this Lipschitz continuity isn't just some theoretical nicety.
It has real practical benefits for the training process.
Exactly. It makes the training more robust and less prone to those instabilities that often plague deep neural networks, especially when you push the limits of complexity.
It sounds like this L2 self-attention could be a game changer.
Uh-huh.
Even be a quest for invertibility.
Yeah.
Any application where stability and predictability are paramount could benefit from this.
Absolutely. This paper really opens up
Yeah.
a whole new avenue for exploring more robust and controllable AI models.
It does, and it raises a fascinating question.
Yeah.
If L2 distance is one way to achieve Lipschitz continuity, what other possibilities are out there?
That's the exciting part. We're really just scratching the surface here. The authors themselves acknowledge that this is just a starting point.
Right.
Might be other distance metrics or architectural innovations that could lead to even more powerful and stable
Wow.
invertible AI systems.
Feels like we've gone down like a deep rabbit hole here.
It has been a journey.
Yeah, from stretchy rubber sheets to the geometry. This paper really stretches the imagination.
It does, and it highlights a crucial point.
What's that?
Progress in AI isn't just about building bigger models or gathering more data. Sometimes it's about taking a step back and examining the mathematical foundations.
And in this case, that examination has uncovered a potential vulnerability in one of the most celebrated AI architectures of our time.
That's true. The paper doesn't diminish the achievements of transformers.
Right.
It simply reveals that even in our most successful models, there are hidden depths and subtleties that we're only beginning to grasp.
And that's what makes this field so exciting.
It is.
There's always another layer to uncover, another challenge to tackle.
This quest for invertible AI in particular feels like a fundamental shift in how we think about intelligence.
If we can build models that can not only process information,
Right.
but also deconstruct it and reconstruct it,
Yeah.
doesn't that bring us closer to understanding the very essence of thought?
It does. It raises profound questions about the nature of learning, memory, even consciousness.
Imagine being able to trace the flow of information through an AI's mind
Yeah.
to see how it arrived at a particular conclusion. That's a level of transparency and explainability we can only dream of today.
It is, and the potential applications are staggering.
Like what?
Think about lossless data compression,
Okay.
where you could squeeze information down to the bare minimum without losing a single bit.
Wow.
Or imagine generating incredibly realistic synthetic data with like precise control over every aspect.
And as you mentioned earlier, the implications for fields like drug discovery are mind-blowing.
They are being able to like reverse engineer the process of molecular design.
Yeah.
Could lead to the development of entirely new classes of drugs.
Wow.
Tailored to specific targets with unprecedented precision.
This paper has really opened my eyes to a whole new realm of possibilities, but it also leaves me with a sense of wonder.
Yeah.
And a healthy dose of caution.
As with any powerful technology, we need to proceed with both excitement and a deep awareness of the ethical implications.
Ensuring that these invertible AI systems are developed and deployed responsibly will be paramount.
We need to anticipate the potential risks and challenges. Yeah. And establish robust safeguards.
Well, on that note, I think we've reached the end of our deep dive for today.
We have.
But the conversation, it seems, is just beginning.
This is a call to action. A challenge to the AI community to explore the uncharted territory of invertibility.
And as we venture into this new frontier, we must do so in a spirit of curiosity, collaboration, and a commitment to building a future where AI serves humanity in all its complexity.
Indeed, the journey ahead is bound to be filled with surprises.
Oh, yeah.
Setbacks and ultimately transformative breakthroughs.
To our listeners, we leave you with this final thought.
Okay.
As we unlock the secrets of invertibility, we're not just building more powerful machines, we're deepening our understanding of ourselves.
And that's a journey worth taking.
Absolutely. Thanks for joining us on this deep dive. Until next time.